In this tutorial, we will look at the 3D diffusion problem of the using numerical methods, and there is a source in this case as well. So the problem given in your tutorial is about a 10 by 10 by 10 room where the ambient temperature is 25 degrees Celsius, and there is also a vent on one of the walls that is closed. And in the middle of the room, we turn on a computer at t equals 0, and that computer produces about 1 kilowatt of heat power, or in other words 1000 joules per second of energy. And what we want to do is want to find out how is the temperature of the surroundings evolving over time because of this source. And the specific heat of air is given, the density of air is given, and then thermal conductivity of air is also given. So what we need to find out is that what happens when the computer is on for 5 hours first, and then the second part is the computer is on for 10 hours, but after 5 hours from the beginning we open the vent, and we are just the way we are setting up the vent is that we are assuming a temperature, this should be a temperature of 20 degrees Celsius at the vent, so it will start to cool down the room, and we are ignoring advection in this case, which will be covered later, but for now we're not going to assume anything about the movement of the air in the room. So with these things given, I do want to point out that although the thermal conductivity is given to be 0.07257, and since there is no advection, to speed up the process we will make this 100 times, so 2.57, and that will improve our visualization of the event, but in reality there is also advection, which is contributing to the spreading of the temperature throughout the room. So what we will do is we will take our 2D problem that we have already created and save it as a 3D file, and we will make changes to this file. So some of those things need to be updated. So we found that rho is 1.205, CP is 1.005 kilojoules, so that would be 1005 joules. K is not relevant at this point because it's going to be an array. We would like to have a room insulated, so Lx, and we add Lz equal to 10, and similarly here we can add Nz equal to 51, and as you can see this is going to be become a really complicated problem, so we will reduce all of these to 21 so that we have a little bit smaller size of the array. And here we are running it for 500 seconds, but what we want is we know we have to at least run for 10 hours. So let's say 15 times 3600. So what would that be? How many iterations are those? We want to run it for 54,000 seconds. So maybe if we are running it every 30 seconds, if we change our dt to 30 seconds, then we need at least 1800 iterations. So we'll put maybe 3000 iterations here. And similarly here we will have dz Lz divided by Nz minus 1. Okay. CFL, we want to run this code at a little faster speed, so we will change this. We'll actually just set up dt at this point, dt equal to maybe 20 seconds. Okay. And now our matrix, we have been using ny first, but now because we're in the 3 dimensions we will stick to the nx, ny, comma, nz. And similarly we will create the Z line space, and then also create a three-dimensional location or mesh matrix. Okay, so we keep doing that, and then our K is going to be nx times ny times nz matrix. And what we want to do is we want to put the boundary of this K matrix to be insulated, so very small K values. So what we will do is we'll say, okay, the first side is equal to 0. Maybe 0.001, very small value, and then because we want the other side to be the same as well, so we can just add here and then this will do both sides to be 0.001. So this is along x-axis, but we want to repeat the same thing for y-axis. And z-axis. So what we are telling it that all around the room we have low thermal conductivity. So when we run the computer, the field will not go past the wall, or it will go past at a very small rate. And here we need to initialize, and we know that the temperature of the initial temperature is 25, so we'll put 25 here. And notice I have increased another semicolon, another column there to indicate that it's a three-dimensional matrix. And in this case, I'm going to assume that dx and dy and dz may be different. So I'm going to show you another way of solving this problem. So first of all, we have to add another for loop here that represents the k dimension or the z dimension, and then corresponding end command. And now we have a three-dimensional matrix which is I, J, and K. So the new temperature value at I, J, K is the old value at I, J, and K plus something which is dt times the constant, which is the thermal conductivity at I, J, K divided by rho divided by Cp. And then after that we multiply this with this derivative, but we're going to change this. First of all, we're going to do the derivative along x-axis plus derivative along y-axis plus derivative along z-axis separately. So right here, let's start that. So the derivative, the second derivative with respect to x-axis is we multiply it with dx squared, but in here we have tc, and we take the derivative along x-axis, so that will be I plus 1 jk minus 2 times I j k, and then plus this same thing but on the other side, the other node, which is I minus. So as you can see, this is the second derivative with respect to x-axis. Now we need to add to this the derivative with respect to y-axis. So I'm just going to copy paste this, and instead of I plus 1 I have j plus 1, and over here instead of I minus 1 I have j minus 1, and over here I have dy and dy. Now I need to add one more term for z-axis, which again I will just copy paste this over here, and now I have k plus 1 and k minus 1, and over here the differentials will be dz and dz. So this is the numerical implementation of the three-dimensional diffusion equation, but in this case I'm explicitly putting dx, dy, dz so that you can see that these can be actually different values, and they can be implemented if they're different as well. So the next part comes to what is the source in this case. So we have the source, and it's sitting in the middle of the room, so we can assume that it's sitting in the middle index. So our index is 21, so we can along xy direction we can treat it as 10 10, and along z direction we will put it at 2 because 1 is insulated. So here we can say that the source is at 10 comma 10 comma 2, and so we want to add the source to this, and the source is dt times the value of the q, which is 1000, divided by rho divided by cp. And now we don't want this to be present all the time, so in the first case it's for 5 hours, so we say if t is less than 5 hours, which is 5 times 3600, so that's that many seconds, then add the source, otherwise it won't add the source. And the boundary condition for this, again, we have to make it we're going to make it insulated boundary, which is this last part, and we want to do this for each edge. So let's say this one is for x-axis, so that's the last edge along the right edge along the x-axis. But we also need to do the first edge, which will be 1, and that would be equal to 2. We need to repeat this for all edges. So in this case we'll have for the y-axis, and then again here for the y-axis, and similarly we repeat this for the z-axis, and for the other side of the z-axis. This is very similar to what we did earlier for the 2D case, but in this case we are doing it for the 3D case. Oops, that should be on this side. So what we are saying is that this for example, this one is the top, this is the roof, this is the floor, and this is the roof. Floor and roof, and then these are the 4 walls. So all of these are insulated, and then in order to visualize it, we can't use mesh anymore, so we'll have to use something else. We have learned that we can try a slice command, and so let's put slices instead of mesh. And what we give to slice command is the scalar field, which is x, y, z, and the scalar field, and then we also tell it where we want the slices to appear. So we can ask the slice to appear at if x is equal to 5, and then another one at y is equal to 5, and maybe nothing along the z direction, or we can put one at maybe 2. Now we can, for now, comment out the gradient part, because we may not need this yet, and comment out the subplot. And also don't forget that there's a value of k that we need to add, 0.0257 times 100. And I know we put 20 seconds there, try 10 seconds because I realized that 20 seconds might be a little high value, and then run the code. And you will see how for the 3D case these slices are showing you the evolution of temperature, starting with the source in the middle, and then how it it has run for 90 minutes now, and